So welcome to the TCS Plus talk. We are very excited to have Shravas Rao speaking today. Shravas is currently a postdoctoral fellow at Northwestern University. Before this, he completed his PhD at New York University. And I would like to thank Shravas for speaking at the seminar today. And today we will hear about degree versus approximate degree and quantum implications of Huang's sensitive theorem. Please take it away.
Awesome. Thanks for the introduction. Thanks for inviting me. I've been a huge fan of TCS Plus for a while, so it's definitely exciting to be speaking here today. So as Sumega said, I'll be talking about degree versus approximate degree and quantum implications of Huang's sensitivity theorem. This is based on joint work with Scott Aronson, Shalov Ben David, Robin Kothari, and Avishai Tal. I should also, maybe point out that, Huang wasn't a co-author of this work, but, as we allude to in the title, none of the results that appear in this work would be possible without Hao Huang. So, he was definitely a big contributor to this work being possible. Cool, so I'll go ahead and get started by giving a summary of results. I'm going to use a lot of terminology when I go through the summaries, and I'll sort of define some of these terms as I go through, but maybe it will be helpful to have a brief sort of overview of what we'll talk about today. So the main player today are Boolean functions. These are functions that take in a string of zeros and ones and output a 0 or a 1. It's going to be really important in this talk that our functions are all total. What this means is that, for every input, there is output. Well, in particular, a lot of, situation is different when we don't have total functions, when we say we have partial functions, when, there are some inputs with no output. We have two sets of results. The first set of results sort of follows from this relationship between degree and quantum query complexity. In this work, we show degree is bounded above by quantum query complexity squared. What follows from this is that the deterministic query complexity is bounded above by quantum query complexity to the fourth, and also the quantum query complexity of any non-trivial monotone graph property at n vertices is omega of n. Right, so this is a property where if you add edges, you'll still satisfy that property. Cool. The second set of results relates degree with approximate degree. In particular, we show that degree is bounded above by approximate degree squared. One application of this is that the approximate degree of any read ones formula on n variables is omega of square root of n. Cool, so as I mentioned, the main player in today is going to be Boolean functions, total functions that take in a string of zeros and ones and output of the 0 or 1. It might be helpful to have just some examples of what some of these functions might look like. So I'll go ahead and give some examples. The first example is a dictator function. The dictator function just outputs the first bit of the input. Right, so in some sense, the dictator function kind of, is dictated by the first input. We also have OR, right? The OR function sort of outputs a 0 if all of the input bits are 0. But if any single one of the input bits is 1, then it outputs a 1. Well, the last example I'll mention is XOR. XOR adds up all of your bits. If your sum is 0, if your sum is even, the output is 0. If the sum is 1, it's odd, then the output is 1. Right, so XOR will output the parity of the sum of your input bits. Cool. I'll start by talking about deterministic query complexity. And the deterministic query complexity of a Boolean function is the number of deterministic queries required to compute f on any input. And it's important that these queries can be adaptive. Right, so you can think about, how can you compute f by reading as few bits as possible. In the case of dictator, the deterministic query complexity is 1, right? Because all you need to do is, read that first bit, and that first bit will tell you the output of your function. It doesn't really matter what any of the other bits are. For XOR, you do need to read all n bits. You need to look at all n bits because, even if you've looked at n minus 1 bits, that last bit can determine your output of the function XOR. The situation with OR is a little bit complicated, right? Because, as soon as you see a 1, as soon as you see a 1 in your query, then, you can output 1. But in the situation where, the first n minus bits are all 0, that last bit will still determine the output of your function. So in this case, you do need to actually read all inputs. Cool. In addition to deterministic query complexity, we also have quantum query complexity. Cool. So the quantum query complexity of a Boolean function is the number of quantum queries needed to compute f on any input. And we allow an error of at most 1/3. If you've seen sort of quantum query complexity, but you only vaguely remember it, you can remember that, what we do is we start with a quantum state. We apply a quantum query operator, we apply a unitary operator, a quantum query operator, and so on and so forth. And then in the end, apply a measurement. I think if you haven't seen quantum query complexity before, what I'll say is that, I think you can still get a lot of this talk without knowing, how exactly quantum query complexity works. And, maybe you haven't seen it before. At the very least, that quantum is a big deal. If you're on the job market like me, you might have noticed that a lot of places are looking for people who do quantum specifically. So I think you'll still be able to get a lot out of this talk, but I think there's maybe not enough time to really go into detail about what exactly is going on when we're talking about quantum query complexity. Cool, but we can talk about the quantum query complexity of these functions. For dictator and OR, we get about the same number of queries required, right? For dictator, we need we can get away with one quantum query. With XOR, we can actually get away with n/2, but we can't do better than that. For OR, we can actually do significantly better than n quantum queries. We can actually do square root of n quantum queries. And this is due to an algorithm by Grover, and this is square root of n is tight due to a lower bound Cool. So we can ask this question about, what is the relationship between deterministic query complexity and quantum query complexity, right? And this question is going to be it's pretty significant because, it kind of gives us it tells us in some sense, what is the power of quantum computation in relation to deterministic computation, right? Of course, in this query model, but this is sort of one step in understanding, what is actually the power of quantum computation. Cool. So this question about deterministic query complexity and quantum query complexity was first explored in this work by Nissan Szigeti, and then improved in Beals, Merman, Cleve, Mosk, and DeWolf, right? And so the situation before this work was that deterministic query complexity is bounded above by quantum query complexity to the 6th power. This work is able to improve that power 6 relation to the power 4 relation. Right, so deterministic query complexity is bounded above by quantum query complexity to the 4th. And this relationship is tight due to an example due to Ambinas, Balotis, Balovs, and Leaves, Santa, and Smatrovs. Well, they actually give a function where the deterministic query complexity is quantum query complexity to the 4th.
So can you say in a few lines, what's the function?
No.
Okay.
Yeah, sorry.
Yeah.
Cool. So as I mentioned in the introduction, right, so the tool we'll use to sort of, this relationship between deterministic query complexity and quantum query complexity, right, it was in this first set of results where it comes from relating degree to quantum query complexity, right? So basically degree is going to be a major player in relating deterministic query complexity and quantum query complexity. So I'll talk about degree. The first thing to note is that any Boolean function can be represented exactly by a polynomial. Cool. That means that there exists for any Boolean function a polynomial, so that the inputs to the polynomial, if you feed the inputs to your Boolean function also to your polynomial, the value of the polynomial is equal to the value of your Boolean function. Cool. This you can come up with this in a few different ways. One reason is that there's only a finite number of inputs to a Boolean function. Cool. So the degree of a Boolean function is the degree of its polynomial representation. Cool. So in particular, if we look at every single monomial, we look at the monomial with the most number of terms. That's going to be the degree of our Boolean function, right? We can do this because our inputs are 0 or 1, so only powers of 0 or 1 matter.
So there's a question: are we using 0, 1 or 1 minus 1 as the bit representation?
Yeah. So we'll use 0, 1 for now. At some point later in the talk, I'll maybe talk about switching to 1 minus 1. But for now, we'll stick with 0, 1. Cool. And one way to think about degree is that it can be kind of like a proxy for deterministic query complexity. Cool. In particular, degree is a lower bound for deterministic query complexity. Cool. So it might be helpful to sort of consider an example. So we can talk about the degree of OR. Right? And OR is this function where it's 0 if all our input bits are 0 or 1 otherwise. Cool. And it turns out we can actually represent OR by this polynomial that is on this slide on your screen. Right? If all your input bits are 0, then 1 minus xi will always be 1. The product will be 1, and 1 minus 1 is 0. If any single one of your input bits is 1, then the product will be 0, and the value of this polynomial will be 1. Right? So this is a polynomial that matches the action of OR. Cool. And the degree of this polynomial is n, and the degree of OR is therefore n. Right? Maybe I should have mentioned this in the last slide, but you can show that there's a unique polynomial representation for any function. Cool. So the other player in this proof between degree and quantum query complexity, and also deterministic query complexity, in deterministic query complexity and quantum query complexity, is this notion of spectral sensitivity. Right. So this notion of spectral sensitivity, I think, it had appeared in previous work, was used implicitly in Huang's work, and we really rely on it a lot in this work. Cool. So the spectral sensitivity is defined as follows. The spectral sensitivity of a Boolean function f is the largest eigenvalue of the matrix defined as follows. One thing I'll say is that when we're talking about matrices, it's helpful for me to index rows and columns by vectors, elements in 0, 1 to the n. If this is maybe new to you, I think one thing you can also do is maybe consider indexing your rows and columns by binary numbers, and it's essentially the same thing. We have a 1 in the xth row and the yth column. If x and y differ in exactly one coordinate, and f of x is not equal to f of y, and it's 0 otherwise. Well, and the spectral sensitivity is going to be the largest eigenvalue of this matrix. One way to think about this matrix is that it is the adjacency matrix of a subgraph of the hypercube. And in particular, it's a subgraph constructed by the function, sort of based on the function f. Right? In the hypercube, we have a 1 if x and y differ in exactly one coordinate. And this A of f is the adjacency matrix where we keep those edges that go between a 0 input and a 1 input, and we remove edges that go between a 0 input and a 0 input and a 1 input and a 1 input. Cool. So we can look at the spectral sensitivity of, say, OR. Right, and I have on the right-hand side of this block, the hypercube on 0, 1 to the 3. Right, and OR is going to be 0 if all our input bits is 0, and 1 if all the input bits are, if any input bit is 1. Cool. So we have an edge between 0, 0, 0 and 1, 0, 0, 0, 1, 0, and 0, 0, 1. Because these are the edges that go from a 0 input to a 1 input in the hypercube. Cool. All the other edges in the hypercube, go between 1 input and a 1 input. So we don't consider those edges, and we can construct, A of f by considering the adjacency matrix of this subgraph of the hypercube. If you sort of, consider the general case of A of f for OR, what you'll end up getting is this matrix where in the first row, the row corresponding to the all 0 inputs, you'll have a 0 and then a bunch of 1s. And the column corresponding to all 0 inputs, you'll have a 0 and then a bunch of 1s. And everything else is 0. Cool. And in particular, you'll have also a bunch of 0 rows and a bunch of 0 columns. But I didn't include them in this picture of this matrix. Cool. And then if you compute the largest eigenvalue of this matrix, you'll get that it's square root of n. And so the spectral sensitivity of OR is going to be square root of n. Cool. So both spectral sensitivity and degree are going to be sort of these big players and sort of determining the relationship between deterministic query complexity and quantum query complexity. Cool. So I'll start by talking about the relationship between degree and quantum query complexity of f and quantum query complexity. The proof goes as follows. We start by upper bounding degree by spectral sensitivity squared. This is due to Huang.
Sorry, can you go back a slide?
Yeah.
So is it, so the size of the matrix here is 2 to the n, cross 2 to the n, and then you're saying it is actually square root n, this the largest eigenvalue?
Yeah, yeah.
Oh, I see. Okay.
Right. One way kind of to sort of put this in perspective is that the largest eigenvalue of the hypercube will be n, because the degree of every vertex is n.
Okay.
Right. So this is going to be a subgraph of the hypercube, so it'll be like less than that.
Okay.
Cool. So the first step is to bound degree by lambda squared, and that's due to Huang. I think this is sort of implicit in Huang's proof, but it's there. What we do is we bound lambda by what's quantity you get from applying the spectral adversary method to F. And then what Barnum, Sachs, and Szigeti showed is that what you get when you apply the spectral adversary method of F is bounded above by the quantum Curry complexity of F. Cool. I think for this talk, I won't go too much into the spectral adversary method. I guess one thing I'll say is that you can actually prove this statement from consequence of the second set of results, and I'm going to focus more on that. Maybe what I will say is that the quantity you get from applying the spectral adversary method is also some sort of matrix quantity. So I think the proof that you can bound this above is a little bit straightforward. But I'll mostly focus on sort of you can actually retrieve this result from applying the second set of results that I'll talk about later. Cool. So this is the bound. This is how you can bound degree by quantum Curry complexity squared. And once you have that, then you can bound deterministic Curry complexity by quantum Curry complexity to the fourth. Right, and this again will rely on older results. We start by bounding deterministic Curry complexity by Bloch sensitivity times degree, which is through the Midrahanis. Then we can bound Bloch sensitivity from above by quantum Curry complexity squared. And then, as I said earlier, we can bound degree above by quantum Curry complexity squared. Cool. And once you just put all these together, you get a upper bound on deterministic Curry complexity. Cool. And the other consequence of degree versus quantum Curry complexity squared I had mentioned was this Andrea Karp-Rosenberg conjecture. Right. So what we're able to show is that the quantum Curry complexity of any non-trivial monotone graph property on n vertices is omega of n. Cool. So you can think of, say, connectivity or K-clique. These are examples of properties where if you add edges to your graph, you're still going to satisfy that property. Cool. And again, the proof, once you have this relationship between degree and quantum Curry complexity, and the proof kind of follows from sort of known results. In particular, Dodas and Khanna show that the degree of any non-trivial monotone graph property is omega of n squared. Cool. So then it will follow that this is a lower bound of quantum Curry complexity. We can get a lower bound of quantum Curry complexity. One thing that's a little bit interesting is that there's also a randomized Curry complexity version of this conjecture, right? So what I should mention is that this is tight. One reason why this is tight in the quantum Curry case is you can think of the graph property, does your graph contain an edge? And in this case, a Grover search does, only require n queries. So this is tight in the quantum case. In the randomized case it's not tight. The best, lower bound we get is n to the 4/3, and the conjecture is, we can get n squared, which is a little bit interesting because I think, usually we think of, the quantum versions of problems as being harder, but in this case, we actually know the answer for the quantum version of this conjecture, but we don't know the right answer for the randomized version of this conjecture. Cool, so that's it for the first set of results. Now I'm going to move on to the second set of results that relates approximate degree with degree, and I'll spend most of the rest of the talk talking about this set of results. Cool, so we say a polynomial P epsilon approximates a Boolean function f if the absolute value of the difference on every single input, every single Boolean input is bounded above by epsilon. We also will just require, for sake of the definition, that P of x is in the range between 0 and 1, right? But we need our polynomial to sort of get close to the actual value on every single Boolean input. Cool. When we talk about approximate degree in general, we're going to say the approximate degree of a Boolean function is the smallest degree of a polynomial that 1/3 approximates f. Right. So in this case, we'll tolerate an error of, say, at most 1/3. And one reason, there are a lot of reasons why approximate degree is super useful. One reason why approximate degree is useful is that Beals, Berman, Cleve, Mosca, and DeWolf showed that approximate degree is a lower bound for quantum query complexity. Cool. So this is nice for people like me who still, they're still a little bit new to quantum, because, if you're thinking about the quantum query complexity of a function and you're like, I don't really know what to think about, well, you can maybe focus on, say, approximate degree. Right? An approximate degree often will sort of give you a sense as to what is going on with quantum query complexity without having to really worry about quantum. You can instead worry about, what is a polynomial that can approximate my function. Cool. So I'll do an example for OR. We can do an example. So what I have up here is sort of the polynomial that computes OR exactly. The best polynomials that say 1/3 approximate OR are a little bit complicated, but we can look at the situation with 2 inputs where we have x1 and x2, and in this case we can approximate OR by the polynomial 1/3 plus 1/3 x1 plus 1/3 x2. Right? If both of our inputs are 0, then the value of this polynomial is 1/3, which is close to 0. If one of our inputs is 1/3, then our value of this polynomial is 1. Then the value of this polynomial is 2/3. And we're close to 1. If both of our inputs are 1, the value of this polynomial is 1, which is close to 1. In general, you can there's a construction that approximates OR that has degree square root of n using Chebyshev polynomials. Another way you can sort of get this, get the fact that the approximate degree of OR is a square root of n. If you know, say, Grover's algorithm, is that if you remember the proof that approximate degree is bounded above by quantum query complexity, what they do is, they look at a quantum query complexity, let's say algorithm, they basically extract a polynomial from that. So since Grover uses square root of n queries, you can extract a polynomial from Grover's algorithm that has degree square root of n. So that's another way you can get an upper bound on approximate degree of OR. Well, and then there's one more thing I forgot. So I want to just go back one slide, which is that, right. So Beals, Berman, Cleve, Mosca, and DeWolf prove that approximate degree is bounded above by quantum query complexity. What we show in this work is degree is bounded above by approximate degree squared. So if you combine these two results, you'll get another proof that degree is bounded above by quantum query complexity. Right, so this is one. So we did one version of this earlier, but this is another way you can get bound on degree in terms of quantum query complexity. Cool. So I want to sort of talk a little bit about the history of degree versus approximate degree. So this was explored by Nissan Szigeti and also Beals, Berman, Cleve, Mosca, and DeWolf. And the situation before this work was that for total Boolean functions, degree is bounded above by approximate degree to the 6th power. And what we show is that degree is bounded above by approximate degree squared. And this is tight. We can't really improve on this. This is because of OR. OR has degree n, but approximate degree square root of n. Cool. Before talking about the proof, I want to talk about an application to Reed-Once formulas. Reed-Once formula is a formula with and, or not gates in which each variable appears exactly once. Cool. So I have an example up here, right? So if you sort of, construct or write the formula that's represented by this tree, each variable appears only once, and we're using and, or not gates. Cool. And one corollary of this work is that the approximate degree of any Reed-Once formula on n variables is omega squared of n, which is tight. There are actually, you can get this from algorithms that sort of compute Reed-Once formulas, quantum algorithms that compute Reed-Once formulas. But the proof of this just follows from looking at the degree of any Reed-Once formula on n variables. Right. If you look at the degree, you can sort of figure out that the degree is n, and that sort of gives you the approximate degree of a Reed-Wunsch formula. Cool. And I think this is a little bit interesting because, there were a lot of work before this that kind of looked at, specific types of Reed-Wunsch formulas, and were able to get, bounds on the approximate degree of these specific types of Reed-Wunsch formulas. And their proofs were a little bit involved. But, basically, once you have this relationship between degree and approximate degree, well, you can use the degree of a Reed-Wunsch formula to sort of get a bound on the approximate degree of a Reed-Wunsch formula. Cool. So I'll talk about the proof, sort of a relating degree versus approximate degree. Right. So, we show that for all total Boolean functions, degree is bounded above by approximate degree squared. And again, we are going to really rely on Huang's proof of the sensitivity theorem. Implicit in his proof was that degree is bounded above by lambda of f squared. Right. And our contribution is that lambda of f is bounded above by approximate degree of f. And once you combine these two, you get the relationship between degree and approximate degree that we promised. Cool. So what I'll do for the rest of this talk is sort of focus on this question of bounding lambda of f by approximate degree of f. And I think what I'll say is that, our proof isn't as simple as Huang's proof of the sensitivity theorem. So I think, if you don't know it, I think there was a TCS Plus talk where he talked about the sensitivity theorem. So I think, forget exactly how it went, but it wouldn't be surprising if you did the entire proof there. I think our proof is still pretty simple, where you bound lambda above by approximate degree, but maybe not simple enough to go through the entire proof. But hopefully I can give you a lot of the elements that go into it, so that you have a good sense of what goes on. Cool. But what I'll do for the rest of the talk is bound lambda of f by approximate degree of f. Cool. And what I'm going to do instead of focusing on approximate degree is I'm going to first focus on bounding lambda of f by the degree of f. Right. So this is right. So this isn't going to be exactly what we want, but degree is usually simpler to work with. And it turns out that once you have a bound on lambda in terms of degree, you can sort of modify the proof to get a bound for lambda in terms of approximate degree. Well, so it'll be nicer to first work with lambda and degree. Cool. And the way we'll do this is as follows. We're going to start by relating this A of F matrix with A of H, which is the adjacency matrix of the hypercube. Right. So we know, as I mentioned in the definition of spectral sensitivity, the matrix that we look at when we're talking about spectral sensitivity is a subgraph of the hypercube. Right. And what's kind of difficult about A of F is that, it depends on F. It can be anything. But we know A of H pretty well. We know sort of its eigenvectors. We know its eigenvalues since the hypercube is a fixed graph. Right. So if we can understand how A of F relates to a matrix that we understand really well, that can maybe give us a sense as to what, A of F looks like. The next thing we'll do is we'll rather than looking at the standard basis, we'll use the basis of eigenvectors of A of H. Right, this will be helpful because if we start with A of H and we look at the set of eigenvectors, then our matrix will be diagonal. And then what we'll do after that is we'll bound the value of V star AF of V times for any unit vector V. Right, rather than maybe looking specifically at the largest eigenvector, we'll find an upper bound on this value. And since A of F is symmetric, this will give us a bound on the largest eigenvalue also. Cool. So I'll go through each step individually. Cool. So the first step is to bound A of F with A of H. Right. So just to remind yourselves, A of F is this matrix where it's equal to 1 if x and y differ in one coordinate, and we also have that f of x is not equal to f of y. A of H is just going to be the matrix where we have 1 if x and y differ in exactly one coordinate. Right, but since A of H doesn't depend on F, there's no extra condition. When all of the other entries of A of F and A of H are 0. Then in this case, we can think about what does A of F look like in terms of A of H. A of F is going to be exactly what A of H is, except if f of x is not equal to f of y, then it's going to be, you're going to change that 1 to a 0. right? So we can, if we're looking at a of f of x comma y, we can start with a of h of x comma y, and then sort of, subtract a of h of x comma y if, the value of f of x is not equal to f of y. Right? And we can do this by just multiplying by 1 minus 2 of f of x, 1 minus 2 of f of y. Well, at this point, I think we're going to change f to be, say, we're going to change from 0, 1 valued functions to 1 minus 1 valued functions. Right, so if we replace f with 1 minus f over 2, this doesn't change the degree of our function f. But now we can write a of f as a of h minus this matrix, this diagonal matrix with f along the diagonal, times a of h times this diagonal matrix, again, with f along the diagonal. Right, so now the values of f are going to be 1 minus 1. And you can actually define a of f in the same way, right? You're only looking at whether they agree or disagree, right? So, we're going to multiply rows of a of h by the values of f and also columns of a of h by the values of f, which ends up, multiplying, a of h of x comma y by 1 if they differ and minus 1. Sorry, 1 if they don't differ and minus 1 if they differ, which will cancel out from the original a of h. Cool, but what we have now is we have an expression for a of f in terms of a of h. In particular, we start with a of h, and then we kind of perturb it by multiplying a of h, by adding the second matrix where we have a of h and multiply on both sides by diag of f. Cool, the next step is to change the basis to the eigenvectors of a of h. And I'll talk about this in sort of a general sense. What we'll need is sort of to really talk about this is what are the eigenvectors of a of h. But for now, I'll just talk about, and I'll talk about this later. But for now, I'll just talk about what does it mean in a general sense? What happens when we change the I basis to an eigenvector of a of h? Cool. So just to remind ourselves, we have this expression for a of f. Right, we have a of f, 2 times a of f really is equal to a of h minus diag of f times a of h times diag of f. Right, so if we change our basis to eigenvectors of a of h, right, in particular a of h is going to be equal to hxh, where h is the basis of eigenvectors and x is a diagonal matrix containing the eigenvalues. Right, so if we multiply on both sides by the basis of eigenvectors, then we'll get this matrix where we have x, where a of h becomes x. And then the second matrix we have will be sort of this h diag of x, h, x, h diag of h. Right, so this is helpful because now we're not modifying a of h, but we're actually modifying a diagonal matrix. Right, we're starting with x, and then we're sort of modifying x by subtracting this other matrix from it. Right, now we have a diagonal matrix, which is nice because diagonal matrices are easier than even just to think about than even just sort of fixed matrices. Cool, and the last thing we'll do is we'll bound v star af of v from above for a unit vector of v, right? Rather than thinking about eigenvalues, we'll sort of focus on bounding v star af of v for a unit vector v. And this will give us also an upper bound of the largest eigenvector, our largest eigenvalue. Right, so we have this expression for what our a of f matrix looks like, but now in the basis of eigenvectors. All right, and to simplify the above expression, we can let R be equal to this matrix H diag of H. All right, so now A of F is equal to X minus RXR. And we'll focus on, what does this R matrix do? How does it operate? Cool, in particular, we'll show that V and R of V are similar. And this is sort of, it's not a very technical term, right? But one thing to notice is that R star R is equal to the identity matrix. So in particular, R is orthonormal, right? All of its columns are orthogonal to each other. So in particular, that means if we multiply any unit vector by R, we'll get another unit vector. Right, so both V and R of V are unit vectors. We'll show that they're also similar. And this sort of, it's not a very precise word, but we'll show they're similar. And we can show that V and R of V are similar. Then we can show that V star X of V and R V star times X times R V are similar. Right, and if both of these values are similar, then the difference between them is going to be upper bounded. And that means that, V star H A of F H V is going to be upper bounded too. Cool, so really all we need to do is show that V and R of V are similar. And then, once we show that they're similar, we can use sort of this more technical sense of why they're similar to get an upper bound on V star A of F of V. Cool, so what I'll do now is I'll talk about, what is the relationship between V and R of V, right? Where again, R is equal to this matrix where we start with a diagonal, this diagonal matrix where we put F along the diagonal and multiply on both sides by the eigenvectors of the hypercube. Cool, so before we can really talk about R, we come up with R by starting with this diagonal matrix with F, values of F along the diagonal, and we multiply on both sides by eigenvectors of the hypercube, right? So in order to really talk about R any further, we have to talk about, what are the eigenvectors and eigenvalues of the hypercube. Cool, so the eigenvectors are as follows. So we have chi of x is going to be a vector in R to the 0, 1 to the n. Chi of x, the yth coordinate of chi of x is going to be -1 to the inner product of x comma y. Cool, x is also going to be a vector in a 0, 1 to the n. So in particular, we have a different eigenvector for each vector in 0, 1 to the n. Cool, so if you're, right, so these are the eigenvectors of the hypercube. And, you can show that these are also, so these are eigenvectors of the hypercube. If you multiply, chi of x by A of h, this is going to be equal to n minus 2 times the Hamming weight of h times chi of x. Right, so n minus 2 times the Hamming weight of h is going to be our eigenvalue. Right, and our Hamming weight is what we get when we add up all of the xi's. Cool, maybe I'll also mention that this inner product and the definition of chi of xy, if we say chi of x of y is equal to -1 to the inner product of x comma y, the inner product is going to be over, actually it doesn't matter, yeah. I was gonna say it's over F2, but I think it's fine either way. Cool, so now we have the eigenvectors and eigenvalues of the hypercube. And now we can actually talk about R. Right, so sort of what's crucial here is that the x row in the yth coordinate of R is going to be equal to the inner product of F and chi of x minus y, where here the x minus y is over F2. Right, so we have a 0 minus 1 that's going to end up being 1. Cool, so if you're familiar with, say, Fourier analysis, it might be helpful to sort of notice that, these chi's are characters. Right, and the inner product of F with these characters gives us the Fourier transform on F. Right, so what this means is that the rows and columns of R are just the Fourier transform of F. The 0 row is going to have the sort of in the right order. The 0 column is going to have it in the right order. All of the other rows and columns are going to have the Fourier transform of F, but maybe permuted a little bit. Cool, but the proof of this goes as follows. We can remember R is equal to H diag F times H, where H is the matrix whose rows and columns are eigenvectors. So if we look at what happens in this matrix computation, where we look at the xth row and yth column, right? What we'll essentially be doing, because we have a diagonal matrix in the middle, it makes the multiplication a little bit easier. Essentially, what we'll get is we'll get the inner product of chi of x and the coordinate-wise product of F and chi of y. And if we sort of rearrange this around a little bit, this is actually also the inner product of F and the coordinate-wise product of chi of x and chi of y. And there's this really, really nice property of the eigenvectors of the hypercube, which is that if you take the coordinate-wise product of two eigenvectors, you'll get another eigenvector. In particular, if you take the coordinate-wise product of chi of x and chi of y, you'll get chi of x minus y, where again, the x minus y is over F2, so 0 minus 1 is going to be 1. So this means that the inner product of f and the coordinate-wise product of chi of x and chi of y is going to be the chi of x minus y. It's just going to be sort of the inner product of f with another eigenvector of the hypercube. Cool. So what this means is that, one thing to remember is that, if you have a function f with degree of f, then the Fourier transform on sort of say chi of x, where x has large Hamming weight, is going to be 0. Right? All of the Fourier transform is only on sort of those characters with small degree. Right? So in particular, if you look at the Hamming weight of x minus y, and that is very large, that's larger than degree, then r of x comma y is going to be equal to 0. Cool. So what this means is that r is kind of diagonal, right? So, for instance, if you say the degree is of f is equal to 0, then r would be exactly diagonal. But for larger degree, this won't be exactly diagonal, but it will be diagonal in sort of some sense where, maybe say your geometry on the rows and columns are now the geometry of, say, like the hypercube, right, based on the Hamming weight. Cool, but I think this is helpful intuition to have because, basically, because r is kind of diagonal and also r is orthogonal, if you compare v with r of v, then r doesn't really shift the weight of v around very much, right? R of v will shift the weight around because r of is kind of diagonal. It doesn't shift the weight of v around very much. And so because of this, v and r of v will end up being a little bit similar to each other. Right, so in particular, if we compare x star, v star xv and rv star x rv, they'll differ by at most 2 times degree. Right, and the reason but this is that, r doesn't, right, again, r shifts the weight of v around because r is orthogonal, but it doesn't shift the weight of v around by very much because but r is like kind of diagonal. Right, in particular, it will shift a weight sort of, in proportion, by at most, say, like the degree of our function f. Right, if we remember what the eigenvalues of x, our eigenvectors are, we'll think about what x looks like. The value, x is a diagonal matrix. The values in the diagonal are the eigenvalues of our hypercube. And the eigenvalues of our hypercube are sort of related to the Hamming weight of x. Right, so on one hand, r doesn't move the weight around by very much. It moves by a weight sort of in a way that's related to the Hamming weight related to degree. But the difference between sort of, say, two elements, two elements on our diagonal is sort of related to the Hamming weight of those elements, right? In particular, the eigenvalues on our diagonal are related to the Hamming weight of the corresponding coordinates. Cool. So once you have this, you're able to compare v star xv and rv star xrv, and you get an upper bound of degree, and you can get an upper bound basically on spectral sensitivity with degree. Cool. So that tells us that sort of gives us an idea of sort of, say, how to compare spectral sensitivity and degree. Now we can talk about spectral sensitivity and approximate degree. And we can sort of try using the same technique we use for degree. Right. In this case, now we have r, we're going to let it be equal to h diag ph, where p approximates f. Right. So I think now, right, we're shifting to plus minus 1. So p will be sort of, say, close to +1, close to -1. And we can ask ourselves, what properties does R have, right, in this new situation where we're dealing with approximate degree, we're dealing with a polynomial that approximates f. R is still going to be kind of diagonal, right? Because in this proof that R was kind of diagonal, we used sort of the fact that, we use these properties of Fourier transforms of functions with small degree, which sort of is related to P. The issue here is that R is not orthogonal, right? Because this diagonal matrix in the middle now is not +1, -1 valued, but it's going to be values that are close to +1, close to -1. Right? So when we multiply R with itself, we're not going to get back the identity. So R is not going to be exactly orthogonal. It turns out that R, you can think of it as being kind of orthogonal, right? Because it's still, the entries along the diagonal are still like close to +1, close to -1. And sort of if you go through the steps I mentioned before, you'll get that, you'll get a proof where, P doesn't say 1/3 approximate F, but say, I think 1/log n approximates F. And then in this case, you can use, say, function composition. Another technique you can use to also get a bound on spectral sensitivity in terms of approximate degree is sort of, again, use this R matrix and sort of use properties of, say, spectral norm in terms of gamma 2 norm. Cool, but basically, you can use a lot of the same ideas for bounding lambda above by degree to bound lambda above by approximate degree. And sort of, the changes you have to make are to make it work for approximate degree are just a little bit more, but they're just kind of technical issues. Cool, and again, once you're able to bound lambda above by approximate degree, we can use Hao-Huang's proof that lower bounds lambda by square root of degree, and then we get the relationship between degree and approximate degree. Cool, so I'll finish there. So I'll maybe mention some of sort of these, some sort of take-home ideas. So we can bound deterministic query complexity above by quantum query complexity to the fourth. We can also bound degree by approximate degree of F squared, and also by quantum query complexity of F squared. And I think the other thing to really sort of notice is that spectral sensitivity is a useful complexity measure, right? And it's a little bit surprising because it turns out spectral sensitivity was used before Hao-Huang used it to prove the sensitivity theorem. But somehow it just didn't really maybe say attract a lot of attention. And now that we have this, but now it turns out that you can use spectral sensitivity to prove a lot of these relationships between query complexity measures, right? Not just between, say, degree and sensitivity, like how Huang could in the proof of sensitivity theorem, but also use it for degree versus approximate degree, or say deterministic query complexity and quantum query complexity. Cool, I'll mention a couple open problems. So one question you can ask is, what is the relationship between randomized query complexity and quantum query complexity? Cool, so there do exist functions that were only just recently sort of, say, published that show that randomized query complexities can be bounded below by quantum query complexity cubed. There's one function due to Bonzal and Sinha, another due to Shurstrov, Strozenko, and Wu. Right, so the question here is, is the right relationship, say, 3 or 4 or somewhere in between? Cool. Another maybe open question to think about is, what is the relationship between block sensitivity and lambda? Right, and you can ask, what is can block sensitivity, which Hao-Huang showed it's bounded above by lambda f to the fourth be improved. All right, and this would maybe be one way to sort of get the right relationship between block sensitivity and spectral sensitivity. Right, I think Hao-Huang did a polynomial relationship, but we still don't know the exact relationship. Cool. And the last thing I'll mention is that those are just a couple open problems. If you take a look in the paper, there's this really nice table that Robin made that sort of shows the relationships between every pair of between many pairs of query complexity measures. Right. In some cases, we know sort of the right answer. We know both an upper bound and a matching lower bound. But there are examples where we don't know sort of say the right answer, where there's a difference between upper and lower bounds. Cool, but I will end there.
Let's thank Shravan. Thank you for the great talk. Are there any questions? So I'll ask a question. So do you have an intuitive understanding of how sensitive spectral sensitivity is coming into pictures here? It's like, it's surprising that it's so helpful.
Yeah, I think I don't have much of an intuition beyond sort of say what I said, which is, you know, if you sort of put the matrix you get in terms of, say, the eigenvectors of your hypercube. Sort of that's the basis you think about, then, you know, you start with X, you have this R matrix, right, which kind of, you know, has these nice properties where it's like orthogonal and kind of diagonal, or in the case of approximate degree, kind of diagonal and kind of orthogonal. Then, you know, you can get this upper bound. So, but I think, yeah, beyond that, you don't have too much of a great intuition as to like sort of how exactly spectral sensitivity works.
Yeah.
Or at least I think there were some ideas I had, and then it turns out they're like counterexamples that like sort of contradict those ideas. So
I see. Interesting. Yeah. Yeah, thank you. Thanks a lot. It was a great talk. Let's thank Shravis again. Okay.